Please like, share my videos and subscribe my channel if you have not already subscribed. We now discuss the solution of a problem from the section Partial Differential Equations, and this question has appeared in the CSIR National Eligibility Test held in December 2023. The problem is related to the Lagrange's first order linear partial differential equation. This question is from the part C. It is a multiple select question and it carries 4.75 marks. The question ID is 704094. The given question is, consider the Cauchy problem u dou u by dou x plus dou u by dou y is equal to 1, where the ordered pair x comma y belongs to R, the set of real numbers cross the open interval 0 comma infinity, and the given boundary condition is u of x comma 0 is kx, where x belongs to R and with a given real parameter k. So you are given a Cauchy's problem where x comma y, the ordered pair, comes from R cross the open interval 0 to infinity, and the boundary condition is u at x comma 0 is kx, x belongs to R, where k is a given real parameter. Now, for which of the following values of k does the above problem have a solution defined on R cross the open interval 0 to infinity? So we have to investigate the values of k for which this problem has a solution defined on R cross 0 to infinity. So x comes from R and y comes from the open interval 0 to infinity. Let's now discuss the solution of the problem in detail. And here are the options. 4 options are given to us. Right. So the given partial differential equation is the Lagrange's first order linear partial differential equation. This is the equation. Right. Now we write down the auxiliary equations for this first order linear partial differential equation. And now dx by u is the dependent variable, x is the independent variable, y is the independent variable. Right. So dx by u is equal to dy by 1 is equal to du by 1. Agreed. We take a pair of equations like this. Dx by u is equal to du by 1 is equal, and dy by 1 is equal to du by 1. Now integrating, we get integral u du is equal to integral dx is equal to c1 prime, where c1 prime is arbitrary constant, and the integral du minus integral dy is equal to c2. Right. Integral of u du is u square by 2 minus integral of dx is x, u square by 2 minus x is equal to c1 prime. So taking the LCM, we will get u square minus 2x is equal to 2c1 prime. For 2c1 prime, we write another arbitrary constant c1. So integrating, we will get u square minus 2x is equal to c1 and u minus y is equal to c2. Right. Now the general solution of the given partial differential equation is given by u square minus 2x is equal to phi of u minus y, where phi is an arbitrary function. Agreed. You can also write u minus y is equal to some psi of u square minus 2x. That we will do for some other case later in the discussion. Right. We got a general solution. U square minus 2x is equal to phi of u minus y, where phi is an arbitrary function. Agreed. Now, to know the nature of this function, phi, arbitrary function, we use the given condition. So, we are given u at x0 is kx, x belongs to R. That means you put y is equal to 0 and u is equal to kx, where k is a given real parameter. Right. Then u is kx whole square, k square x square minus 2x is equal to phi of u is kx minus y is 0. So now you substitute, put kx is equal to t. Then x will be t by k. Then k square x square will be t square minus 2 into t by k is equal to phi of t. So t square minus 2t by k is equal to phi of t, where t is kx. Remember, k is sitting in the denominator, therefore k not equal to 0. And you cannot put the value of k is equal to 0 in such a discussion. Yeah, you have to take care of that. Right. So now go to the general solution. U square minus 2x is equal to phi of u minus y. Phi of t is t square minus 2t by k. So put t is equal to u minus y. So u minus y whole square minus 2 into u minus y by k. Now expand u minus y whole square. When you expand, u square minus 2uy plus y square, and this u square on the left hand side, that will cancel. Thus you get minus 2x is equal to minus 2uy plus y square minus 2u by k plus 2y by k. Right. Now, so simplify. 2u into y plus 1 by k. These two terms are sent to the left hand side is equal to 2x minus 2x is sent to this side, 2x plus y square plus 2y by k. So now we get the u as 2x plus y square plus 2 into y by k by 2 times y plus 1 by k. Take the LCM. Then you will get k times 2x plus y square plus 2y by 2 times ky plus 1. And this is where xy belongs to r cross 0 to infinity. There should be a comma here. Now remember here, so you got u in terms of k, but here you have to remember k is not 0. That is what you have to remember. So now let's discuss further in the next slide. So that's what we have. So now, what is that we want to do? For which of the values of k does the given problem have a solution defined on r cross the open interval 0, infinity? Right. Let us take k is equal to minus 2. This is option 2. We are trying. K is equal to minus 2. Then uxy is equal to, wherever there is k, you write minus 2. So look at this one, and in the denominator you have minus 2y plus 1. So minus 2y plus 1 will become 0 when y is equal to 1 by 2, and y is equal to 1 by 2 belongs to 0 to infinity. That means minus 2y plus 1 becomes 0 for the value y coming from 0 to infinity. Minus 2y plus 1 becomes 0. Therefore, uxy does not exist. So, option 2 is not true. Let's get into option 3. K is equal to 4. So, wherever there is k, you write 4. And 4y plus 1 exists when y belongs to 0 to infinity. Why? Because y is equal to 4y plus 1 is equal to 0 means y is equal to minus 1 by 4 does not belong to 0 to infinity. Therefore, there is no problem that this 4y plus 1 will create for us. So therefore this exists. This exists for all xy belongs to r cross 0 to infinity. Right. So therefore option 3 is true. Now option 4. Let k is equal to 1. Wherever there is k, substitute 1. And y plus 1 is not 0 for y belongs to 0 to infinity. So this exists for all xy belongs to r cross 0 to infinity. And y plus 1 is 0, y is equal to minus 1, which does not belong to 0 to infinity. Therefore, y plus 1 will not pose any problems to us. Therefore, option 4 is true. Now, we are left with k is equal to 0. And many of them, they say put k is equal to 0 in this, you will get uxy is equal to y. Therefore, the solution exists. That's what the argument they say, but you may be getting the right answer, but that's not the way, because k, what we have taken, is not equal to 0. So we now discuss the case when k is equal to 0. How do we go about it? So I've already told you for this differential equation, partial differential equation, the general solution is u minus y is equal to psi of u square minus 2x, where psi is an arbitrary function. You can also do like this. This is also a general solution. Right. Now put the given condition. U of x comma 0 is equal to kx, x belongs to R, where k is a given real parameter. So u is kx, you substitute. So kx, y is 0, psi of k square x square minus 2x. Agreed. Now put k is equal to 0. Now k is equal to 0. Then psi of minus 2x is equal to 0. That means psi of t is 0 for all t. That's what it says. So therefore the solution is, in this case, u minus y is equal to psi of u square minus 2x. Psi of u square minus 2x is 0. So u minus y is 0. So that is u of x comma y is equal to y, and y belongs to 0 to infinity. The solution exists. And you can verify if you have any doubt. Uxy is equal to y satisfies the given partial differential equation. Why? Dou u by dou x is 0. Dou u by dou y is 1. 1 is equal to 1. So it satisfies the differential equation. And put y is equal to 0. So you will get ux0 is kx when k is 0. So you will get 0. So the given condition is also satisfied. Therefore, note that it satisfies the given partial differential equation and the condition. So thus, for k is equal to 0, the given partial differential equation has a solution. Therefore, option 1 is also true. Thus, the answer to this question is option 1, 3 and 4. That is the detailed discussion of the solution of the given problem from the section partial differential equations, and it is based on the concepts and results of Lagrange's first order linear partial differential equation. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.